not using T2 instead of T1, then it's probably a better approximation. So I wrote down T2. What is T2? Taylor polynomial of degree 2, right? So they look like that. Taylor polynomial requires your base point, and you want to approximate it here at this location, a comma b. Then there's a Taylor polynomial of degree 2. That looks exactly like this, except here a is xk, and y there is yk, right? You're at certain step. To go to next step, instead of using a line, uses a quadratic function to get to the approximate value of the next step. So we use this one, yk, this b value, derivative, and x minus a, this coefficient with 2 factorial, x minus a squared, right? That's the Taylor polynomial of degree 2. Now if you plug in xk plus 1, and difference between these two things is h, so this picks up h, and we have this y prime is by differential equation. This is given differential equation, so xk and yk, if you plug in xk in there, so that replaces that. The problem is y double prime, right? So we have this differential equation looking at y as a function of x. X is our main variable, and here y is a function of x, right? That's how you can look at it. This is how it started before we enter any parameterization. Now, if you differentiate this one more time, and that's going to be y double prime, and so therefore this is d dx here, right? So from this, we're using the multivariable chain rule. Suppose this is parameterized with x. X is x, so it's like x is t. And this one is really complicated, abstractly defined. So fx times the dx dt, but x is t here, then it becomes like this, and fy multiplied by dy dt, x is t, so dy dt can view it as dy dx. If your t is x, then we enter this part here, which is chain rule, multivariable chain rule. Okay? So this y prime can be replaced again with this f of xy, right? Because that was the original differential equation. So the y double prime can be written as a partial with respect to x, partial with y partial multiplied by the right-hand side of the equation. Right? So all these things available from the right-hand side of the equation. Now if you substitute it here with xk in it, then you get this expression right there. So with all that, it becomes k, and this remains the same, and this becomes h squared. So your next value, yk plus 1, is this quadratic expression in h, and xk plus 1 is the same. So if you repeat this procedure, then you get slightly better value than. So how was this one? Did you all realize that you had to use that one before? Yeah, you could be right. Who knows? But I guess it's again bookkeeping. You write. Let's for example that I'm gonna write down that example there, and calculate these things, and make sure that we understand this thing correctly. Was there a question? All right. This was the example. That was. Wait a second. Delete. Okay. This is not part of it. So this is our f of xy, right? All right. So fx is 1, is that right? Fy is negative 2y, correct? So the formula is yk plus 1. Euler's method was really simple, and here is yk plus f of xky. So you plug into this formula there, xk minus yk squared, right? That's what that part is. And h is something was fixed, and here was 0.5 probably, and plus 1.5 factorial, so it's 1 over 2. What is partial x is 1, partial y is negative 2y multiplied by, here's a k, xk minus yk squared, like that, and h squared, right? That's the formula. If you start with x0, 0, negative 1, y0, 1, you plug in negative 1 and 1 on here, and h being negative 0.5, and you get this yk plus 1, which is y1. right? Does that make sense now? Yeah. And xk plus 1 is xk plus h. So this is actual formula. Like everything is explicit here. Does that make sense? Yeah, if you repeat that, and you get to that value that I have there. Any question? And I showed you the picture of it. Looks like this. This is Euler's method. And if you do quadratic, it looks weird, but it's still closer than the Euler's method blue there. And this is with h equals 0.5. This was a homework problem. And if I increase that to 0.2, this is Euler. The red one is Euler's method, and the black one is a quadratic, using quadratic, and the blue one right underneath it is actual solutions. So still doing good. Whenever it's curved a lot, then quadratic method will win. Any question?